Alright, so last part of 7.3, this is called the shell method, and this is kind of neat. This is a Japanese spider crab. You can read a little bit about it down here. But the thing that's neat about it is, look right here. It actually looks like, I mean, that's its face, and it actually looks like Buddha. Grows to over 12 feet wide and lives 100 years. If I'm underwater and I see this thing 12 feet wide coming at me, I don't think I'm going to make it to the surface. I think I'm just going to die right there. Alright, so find the volume of the region bounded by y equals x squared plus 1, y equals 2, and y equals 0 revolved around the y-axis. So if we're revolving it around this axis here, we could actually take it and cut it here, revolve that, and that's just going to be a cylinder, and then we could use the washer method and revolve this part up here and add the two together and find it. But there actually is an easier way. And this is actually set up to find that using the washer method and the cylinder at the bottom. There's the volume of the cylinder. This integral would find the volume of the upper part. You don't have to write this one down. This is just for instance, how you could do it and not have to use the shell method, but it's going to be an intro into the shell method where we'd only have one thing to do. So you end up with 12 pi. Alright, now here's another way we could approach this problem. We could actually take, even though we're rotating around the y-axis, we could use a vertical slice. Now, when we take that vertical slice right there, or that vertical rectangle, it's really thin, and spin it around, it's going to make what we're going to call a shell. Now, it actually makes a tube. So remember, this is hollow. It's not solid. It's just this one strip right here rotated around that y-axis. And that's going to make just a thin little tube that is dx thick, but that goes all the way, and d and this value right here high, that goes all the way around. So if you do these over and over and over, starting here and going all the way out to here, using cylinders, then you're going to rebuild the entire volume that you're looking for. And it would look something like this. Each one of these lines is a new cylinder, or a new tube, I guess you could call it. And we're just building a lot of them. You can't draw all of them, so here's just some examples of them. Alright, now the volume of a thin, hollow cylinder is given by, if you think about it, you can figure out how that thin cylinder is going to be found, because if you sliced it right there and opened it up, what does it become? It becomes a rectangle. Now, what is the width of that rectangle from one side to the other? Well, it's just if we sliced it here and opened it, the width would be the circumference of the circle. And the height would be what? Whatever your function value was at the time. And the thickness of that thing would be your dx. So it's the circumference times the height times the thickness. Well, the circumference is just 2 pi r or pi d, whichever one you want to use. The height is the function value. Now, if you're starting here at the origin and going out, what's your radius for this circle? Well, it's just your x value. and your height is just whatever the y value is for that x value. So that's going to be this right here, x squared plus 1. And the thickness, of course, is the thickness or the width of your slice that you're taking there, which is going to be dx in this case. So putting all that together, you're going to get 2 pi x times x squared plus 1. And then times the dx for thickness. So there is the volume of just this thing right here, this tube that we have. And then if we would integrate it, letting x go from 0 to 2, then we find the volume of the whole thing. And that's where all that stuff comes from. R is equal to x. The 2 pi x is the circumference. The x squared plus 1 is the h. And the dx is the thickness. So adding all those cylinders, tubes, from smallest to largest, we're going to integrate from 0 to 2. Now you'll have to do some simplification here. Notice that the 2 pi is a constant. It can come outside. We'll actually have to distribute the x through here before we can do an integral with by hand. But then it becomes very easy to do. So we end up with 1/4 x to the 4th plus 1/2 x squared, evaluated from 0 to 2, and then multiply that times 2 pi. And when you calculate that, guess what? You're going to get the same value we got before. You're going to get 12 pi. But that one actually turns out to be a little easier in the calculations and everything than the other one did. Now, one thing before we get too far into this, I want you to know the way you do a shell method, notice that our slice is parallel to the axis of rotation. And think back to part 2, the way we did a disc or a washer, our slice was what? It was perpendicular to our axis of rotation. That's a way to determine which one you want to do, where your axis is, what axis of rotation you have, and what's going to be the best way to slice this thing, with a vertical slice or a horizontal slice. If you know that your axis is vertical, but your slice is going to be horizontal for the best way, you're going to end up with a disc or washer method. If your axis of rotation is vertical, but the best way to take the slice to do it in the simplest way is vertical, then they're parallel, therefore it's going to be the shell method would be the best way to work it. And this is the shell method because we use cylindrical shells. And that's what you'll also hear it called by using cylindrical shells when they give you a way to solve a problem, if they tell you specifically how to. Alright, so let's find the volume generated when this shape right here is revolved around the y-axis. Now, the thing is, we're revolving around here. So we're going around that, and we would think, oh, well, it'd be great if we could just do it because, you know, for a lot of people, the washer method makes more sense. So it would be really nice if we could just do the slice right here. There's only one problem. We have one equation right here, and guess what? That describes both this side and that side. So if you do your subtraction of r big R minus little r, in terms of y, it doesn't change. So we have a problem there. So this is one of those that you can't actually do with the washer method. You have to do this one by the shell method. And it's going to kind of look like this when you get it done. There's even some shells there. We can't even solve this thing for x. So we can't use a horizontal slice. So what we want to do is we take a vertical slice. There's an example. And we know that that is going to be the y value, which we already have the equation for. And we know that our thickness is going to be dx. So then we've got our circle to get our tube or cylinder, whichever one you want to call it. Just know that it's hollow. And then we can calculate what everything's going to be. So we know we need the circumference, which is 2 pi r. In this case, our r is once again our x value. And then times the height, which is our -4/9 times x squared minus 10x plus 16. And then our thickness of our slice, which is dx. So there is the volume of 1. And if we integrate, where do we integrate from in 2? Where are we starting our x and where are we ending our x? We're integrating from 2 to 8. We could integrate from 0 to 8, but that's going to include things under here that is actually not part of our graph, because this thing, if you graph it, it's going to continue down here. So be very careful about what you integrate. We're only integrating this part that's above the x-axis, so we're starting at 2 and integrating to 8. So circumference times height times thickness. And when you calculate that, this would not typically be one that they would expect you to do by hand, just because it's not easy to simplify down. Guys, the ones that you'll be expected to simplify to do by hand are going to be pretty straightforward. And when you do this with a calculator, you should get 160 pi. And they're talking about the multiplication right here. All right, so as I said, when the strip is parallel to the axis of rotation, you're going to use the shell method. And when the strip is perpendicular to the axis of rotation, you use the washer method. All right, that's all of 7.3. Make sure you look at all these videos and kind of have a good idea of what we're doing. Make sure you got the notes, and we'll work on some examples in class.